When we left off in our last meeting, we were talking about chemistry, the study of matter, and we were talking about the way we discuss matter or identify it. And we had talked about atoms, molecules, and ions as one way of looking at matter. And then we went on and talked about matter in terms of elements, and we mentioned several things about that. We talked about the symbols, which we say is the alphabet, the chemical alphabet, the abbreviated or the letters that identify the name of each of the particular elements. And by the way, of course, you are responsible to know the symbols, the correct names, etc., and spelling for the elements found in the table in Chapter 1. Not the ones at the end of the text, the 109 elements, but only those that are included in Chapter 1. We talked a little bit about the different types, the monoatomic, mono meaning one, diatomic meaning two, and polyatomic meaning many. But we also looked at some prefixes yesterday that we'll use throughout the semester. And we saw those prefixes in the table in the text that lists the 10 prefixes that we most frequently would encounter. I might mention a little bit before we go on any further here today my idea of how you should study chemistry. Chemistry takes a little bit of diligence from the standpoint of it requires sort of a daily work at it. You can get behind very quickly. In the front of the text, I do have some suggestions on studying. I think it's worth your while reading, but in general, I would scan over the part of the chapter that I think that the instructor is going to cover that day, just briefly, just to have a general idea of what's going to be talked about. After class, I would go back and read the chapter more carefully. Now you have some notes to go with it, and as you go along through the chapters, especially in the problem-solving part, you'll run into an example problem. Like here in Chapter 1, I have an example problem. When you get to that point, look at the example problem. Shortly after the example problem, you'll find an exercise. That exercise is of a type similar to what has been in the example problem. That's a good place to take a break, work the exercise problem, and see if you have really understood what was discussed up to that point. Now, the exercises have not only the answers, but the solutions, detailed with some wording, etc., explaining about what you should have done at the end of the chapter. You don't even have to go to the end of the book. Right at the end of the chapter, you will find the exercises set up and explained what steps you should have used to get the answer. So you can check yourself as you go along. Once you've completed the chapter, and of course there will be problem sets that I will assign that will be turned in, as we mentioned, part of the points of the grading are the problem sets. But immediately following those, then, you will find a chapter self-evaluation. And so here's a chance to take a little test over the chapter material. Take that, and the solutions, not just the answer, but again the solutions for this self-examination will be found in the solutions manual. So not only are the solutions to the odd-numbered problems in here, but also the solutions to the chapter self-evaluations. If you do that on sort of a daily basis, it won't be any problem when you get to test time to be ready for the exam. If you wait until a day or two before and try to go back and cram 2 chapters or so of problem sets in and do them and become comfortable with them, you'll probably have some difficulty. So I encourage spending at least an hour a day on the material that's been covered in class. If you do that, if you don't fall behind, I'm sure that you'll do very well in the course overall. All right, now, continuing on, we're going to move on to one other way that we talk about matter in chemistry, and that is in terms of compounds. Elements are individual atoms, substances. A compound contains atoms of two or more different elements. Two or more different elements. One of the terms that we sometimes confuse are molecules and compounds. Molecules are the combination of two or more atoms, and they can be the same. We talked about nitrogen as a nitrogen molecule containing two nitrogen atoms, N2. That's a molecule. Nitrogen is not a compound. A compound is two atoms, two or more atoms, of different elements. So if we combine a carbon atom and an oxygen atom, we make then a compound called carbon monoxide. So two or more different atoms then makes a compound. Now compounds can be found, again, in molecular form and in ionic form. And I guess I should also mention that compounds are pure substances. Elements are pure substances, compounds are pure substances. So when we're talking specifically about the compound of water, we're talking then about a group of matter that everything is water molecules. That's all that's there. If it isn't, if it has something else in it, then we're talking about a mixture or a solution or something else. We're not talking about a compound. Compound is a pure substance. As I say, compounds can exist as molecules or as ions. For instance, a very common molecular compound is your table sugar, and that is composed of molecules containing carbon, hydrogen, and oxygen. And in the next chapter, we'll look at what chemical formulas tell us what information is there. So, but sugar, a block or a teaspoon of sugar contains sugar molecules. Molecules are neutral species. Atoms are neutral species. But compounds can also be composed of charged species called ions. For instance, your normal table salt is actually ionic. It is composed of a charged sodium particle called a sodium ion and a charged chlorine particle called a chloride ion. And so table salt is not a molecule. Table salt is made up of groups of these sodium charged particles accompanied by chloride charged particles. And in a later chapter, we'll talk about how we can show, how we can identify or determine which of these a compound is. There are some tests that we can do. I have a question, I think, in the back. Was there a question back there?
Yes. Yesterday you said the makeup of the compound, of a molecule, but you didn't specify what the makeup of an ion was. You just said that it had charge. Do we need to know what the makeup of an ion is?
The question was, do we need to know what the makeup of an ion is? A molecule is two or more atoms. We said that. An ion, for our purposes at this point, an ion is merely a charged particle. It may be single charged particle, as we're seeing here. And in Chapter 6, we'll talk about how we form ions, what happens chemically to give us ions when sodium and chlorine come together. But it can also be groups of atoms hooked together that have charges. For instance, we can have an ion which we refer to as a nitrate ion, and the nitrate ion has a chemical formula, NO3, 3 oxygens and a nitrogen hooked together, and that whole group has a charge, a negative charge associated with it. So nitrate is an ion then. It's not a molecule, it's a charged species. So these charged species that we call ions might be monospecies, monoatomic ions, or they might be polyatomic ions, just like molecules are. Okay? Good question. So for now, we just will accept that these appear. When we see them, we'll use it. In Chapter 6, we'll begin to develop the understanding of how they actually do form, okay? Which is part of chemical bonding that we'll be looking at. Another property of compounds is definite composition. That means it's not a haphazard combination of atoms. Water is always 2 hydrogen atoms and 1 oxygen atom. It doesn't make any difference if the water is the water falling out of the sky as precipitation, if it's the water that we're exhaling from our biochemical process, whether it's water that might be formed from burning the gasoline in our automobile engine. As on a cold day you see the exhaust coming out of the tailpipe of a car, that of course contains water. That's what we're seeing, the water that is condensing. But every bit of the water, what we breathe, what the car is putting out, what is precipitating, if we react hydrogen and oxygen in a reactor, all of these have exactly the same composition, the law of definite composition. Water is always 2 hydrogens and 1 oxygen. So nature is not very random. Nature is very specific, and again, as we look in Chapter 6, when we talk about chemical bonding, we'll see why water is always 2 hydrogens and 1 oxygen and nothing else. We'll see why carbon dioxide is always 1 carbon and 2 oxygens, and so forth. Why sodium chloride is 1 sodium and 1 chlorine, not 3 sodiums and 2 chlorines, but it's always 1, 1. Okay? So the law of definite composition when we talk about chemical compounds. All right. Now, one thing that we sometimes interchange or mix or I guess confuse, I would say, is the difference between a mixture and a compound. Remember, a compound is a pure substance. So if I take something like a carton of milk, well, yes, it's all a liquid, but that's not a compound. Milk is made up of water, it's made up of butterfat, it's made up of calcium compounds. It has a whole variety of different chemical compounds in it. There's no definite composition to milk. I mean, if I milk 2 different cows, I get different qualities of milk. I'll get different amounts of butterfat, I'll get different amounts of water, I'll get different amounts of calcium. If I milk a cow in the spring versus the fall, I might get different milk composition. If I go to the grocery store, I can see whole milk, 2% milk, 1% milk, skim milk, and each one begins to look a little bit more like water as you go that way, but there is no definite composition. Milk is a mixture, and we can actually separate components of a mixture one from the other by using physical means. So for instance, in milk, if I want to get out the butterfat, I can spin it, put it in a centrifuge, I can let it set, cream would separate out. If I want to get the water out, I could heat the milk up and boil the water off. I can separate a mixture. I cannot separate a compound by normal physical means. So that's one of the key differences when we talk about a mixture versus a compound. All right? Now, as we go along, we said that chemistry was the study of matter and the changes that it undergoes. And to understand a little bit about the changes that matter undergoes, we have to understand a little bit about some of the properties that we're going to be looking at that allows us to know that changes occurred. How do we know that something has changed? Well, we have to have something then to look at, to focus at, some quality or quantity that identifies that a change has in fact occurred. Well, when it comes to physical properties, these are some fairly common things that we're familiar with, such things as melting point. That's a physical property boiling point. That's a physical property. The density, physical property. So there are a variety, color, taste, odor, physical properties of a substance. So there are a whole bunch. And again, most of these are listed in the text, so I won't bother to write them all up here. Chemical properties are a little bit different. Chemical properties basically is what tendency that a substance has to undergo chemical change. That's a chemical property, tendency to undergo chemical change. Okay? That's what we mean by a chemical property. To give you some idea, if I take a chunk of iron and put it into water, we know that it has a certain tendency to undergo a reaction and form rust. But it's a pretty slow process. So its tendency to react with moisture and oxygen is certainly rather slow. If I take a piece of the metal sodium, in contrast, notice they're not too far apart from each other, sodium number 11 and iron 26. If I take a piece of sodium metal and put it into water, it reacts violently with water. It produces hydrogen gas and explodes. It ignites the hydrogen and oxygen combined from the air and actually explodes. It sets itself on fire. It's a very rapid reaction. So when we talk about chemical properties, that's what we're talking about. What is the tendency for this substance, whether it be an element or a compound, to undergo a chemical change? That's what we're talking about. When chemical change occurs, then we have considerable change in properties that occur. For instance, if I take, and I'll use this example here, sodium metal. If you were to put a piece of sodium metal in the palm of your hand, it would burn a hole through it because you have enough moisture in your skin that would react with the moisture and it would literally burn a hole through. If I take chlorine, element which we mentioned in the previous lecture is a diatomic element, Cl2. If I take chlorine, chlorine itself is a deadly gas. If I inhale some chlorine, I'm probably not long for this world, certainly if I breathe in very much. It's a deadly gas. And I'm going to take those two and react them and form sodium chloride, which is essential for our life. We have to have salt in our diet. We have to have salt to provide the chloride ion to make the stomach acid. We have to have sodium ions to be able to have proper conduction through cell membranes, etc. So here are two things that are totally harmful to us. One of them definitely deadly to us. And when they chemically react, when they undergo this chemical change, their properties are greatly altered. In a physical change, that's not true. Because if you think about a physical change, if I take an ice cube, which is a compound of water, and I take it as a solid and I bite off a chunk and eat it, or if I put it in a glass and let it melt and drink it, there's no difference. It's only the spacing between the water molecules that has changed. Nothing has changed as far as the chemical property of that substance. If I take a taste of sugar, it's sweet. If I put the sugar in water, it is still sweet. Nothing has happened to the sugar molecule. It's still the same. So all we've changed is its distribution. We haven't changed its chemical property. So in chemical change, we actually do change the characteristics of the matter itself. All right. Whenever we're doing change, whether it be physical or chemical, it requires energy. Whether I melt an ice cube or freeze an ice cube requires energy, one way or the other. Either I have to take energy out or put energy in. The gasoline burning in my car is an energy change. That's a chemical process. The carbohydrate undergoing digestion in our body, energy is involved. Every change, whether physical or chemical, is going to involve energy. And by definition, energy is the ability to do work. Okay? Energy is the ability to do work. We have lots of different forms of energy, and energies can be changed from one form to another. We look up here at the lights in the ceiling. We see electrical energy occurring. We see visible. If we put our hand up there, we would feel heat energy. And this is all being produced by a power plant some distance away, which is probably burning coal. So we're taking stored chemical energy from the coal, putting it in to heat water into steam to drive a turbine, which is now mechanical energy, which drives a generator, which converts that to electrical energy, which we run through here to get heat and light. So forms of energy can be interchanged, all right? But it does require energy in any chemical or physical process. Now, as I said, physical change doesn't change the characteristic of matter. Chemical change does. But we often use physical properties to show that a chemical change has occurred. Because it's not always easy to see a chemical change occurring, but oftentimes we can tell that it has occurred because of the physical property changes that have occurred. And let's take a look at a couple of examples of this. If we were to take some nitrogen gas, nitrogen making up about 78% of our atmosphere. Nitrogen gas is a colorless gas. We don't see it in the air. And we were to react it with oxygen gas. Notice that we've written N2 and O2 for each of those elements. Those are diatomic elements. That's the way we write them. When we write down their information, rather than just writing a symbol, we write it as O2. That's the way oxygen exists. It exists as a molecule in the atmosphere, and nitrogen. Now, if we take those two colorless gases and react them with each other, we form a chemical compound. The chemical compound contains one nitrogen and two oxygens. But notice, something has happened. The NO2 is not a colorless gas. The NO2 is a reddish-brown gas. So I'm using the physical property here, the color change, to indicate that something has occurred chemically. When I melt an ice cube, it doesn't change color. It stays the same. There's no color change in the physical change. But there is possibly a color change that occurs when we form one new type of matter from two previous types of matter in a chemical change. So that's one example of something we can look for. A color change is often an indication that a chemical reaction has occurred. Here's another example. Here are two chemical compounds in solution. We have silver nitrate, which is a colorless solution here, and we have sodium chloride. This would be table salt. Colorless solution here. And we're going to begin to pour these two together. So here we're getting ready in this transparency here to pour now the silver nitrate into the sodium chloride. All right? And as soon as the silver nitrate begins to reach the beaker of sodium chloride, we notice the formation of a white, milky-looking solid material in the beaker. So the formation of a solid from two solutions is probably indicative that we have a chemical change occurring. We're forming something new which is no longer soluble in water. From the two things that were soluble in water, indicative then of this chemical change. So we get a nice solid, and that particular solid would be called silver chloride. You don't need to worry about that right now, but it would have a chemical formula of 1 silver and 1 chlorine. AgCl would be the chemical compound that we would have. Well, if we continue on, this just shows we will continue to form the white solid. We will basically get a beaker full of this white, solid, milky-looking material called silver chloride. If we take a couple of common household chemicals, here we have 2. Vinegar. Now, vinegar itself, as a compound, is, of course, a pure substance. It has a chemical formula CH3COOH, a carbon and then 3 hydrogens, a carbon, 2 oxygens, and a hydrogen. That's vinegar. Now, that's actually chemically called acetic acid. And if we put some acetic acid into water, then we produce a solution which commercially is called vinegar. Okay? As a matter of fact, if you look at a bottle of vinegar in the grocery store, you'll see on there it says something like, contains a 5% solution of acetic acid. All right? So, we have household vinegar, and then we have a box over here, Arm & Hammer baking soda. And baking soda is a chemical compound. Its actual name is sodium hydrogen carbonate. It has a chemical formula. It's a little hard to see here, but it's Na, 1 sodium, a hydrogen, a carbon, and 3 oxygens. The name sodium hydrogen carbonate. Now, if we take these two and look at, first of all, their physical states, so we'll put a little bit of each into a beaker here. And of course we see the vinegar is a colorless liquid, looks like water, and the baking soda is a white colored solid material. Now if I pour the two together, then we will get a reaction. What we see here is a foaming, a fizzing occurring. You notice the stream coming into the solid here. We have the obvious evolution of a gas occurring as I mix these two together. This next slide will probably show this a little more clearly. We see here now it is really fizzing up, giving off then, actually what it's giving off is carbon dioxide gas. Now we wouldn't know that, but again we could observe that something process-wise was occurring when we put these two together. What we end up with is not what we started with. It is chemically changed. Okay? I remember as a youngster doing this. Of course, that's back in the days before we had all fancy colored TVs and video games and all that, so we had to look for things to do. One of the things that I loved to do would be sneak in and get the bottle of vinegar, take a Coke bottle, and go out and get some baking soda also, sneak that out of the kitchen. And then we'd go out and throw some baking soda in, quickly pour some vinegar in and smash a cork into the bottle, and then run around and shoot it at each other. So we were actually the early developers of the whatever they call it, paintball, except that we used corks. You could really bounce it off a sister or brother's head. If you could run faster than them and get close, you could really nail them. Or you could shoot it over a tree or whatever you tried to do. But you get a lot of CO2 gas, which of course builds up tremendous pressure in the process, and you could use that then for some sort of aspect. So each of these cases now, we have observed that change is occurring not by being able to see what's happened chemically, but by seeing what is happening in terms of a physical state. So observing physical change, color, evolution of a gas, formation of a solid, etc., is one of the ways that we can tell that a chemical change is occurring. All right, one of the properties of matter that we mentioned was a physical property of matter is density. And this is one of the things that we often do look at from a change standpoint, or to actually identify one type of matter from another. In other words, whether or not we might have a piece of lead metal or a piece of silver metal or a piece of iron, one of the ways we can identify it is by this physical property called density. Now, density by definition is the mass of matter divided by the volume of the matter. All right? The units that we typically use then to express density for solids, notice that the top term in all of these for mass, the unit of mass that we use in science is gram. So each of these has grams for the top unit. The bottom unit for volume, however, is different on the three. For a solid, we typically talk about grams divided by cubic centimeters. Centimeters cubed is what we're talking about there. Now, that means that if we have an object has a definite shape like a square or a rectangle or something like that, we can measure its dimensions in centimeters and we can calculate the volume of the object. We can weigh its mass, and with that piece of information then we can calculate the density. Okay? If it's a liquid or a solution, I just have liquid up there, but this would also be true for solutions. Density of liquids and solutions are given in grams per milliliter. Grams per milliliter. We state this one as grams per cubic centimeter. Whenever we're talking about two relationships like that, we often use the term per. 60 miles per hour, we say we're traveling. All right? That means 60 miles divided by 1 hour. Okay, grams per cubic centimeters. Grams divided by cubic centimeters. And finally, for gas, because gas, the space between particles is so large in a gas. If we take a milliliter, we have so small amount of mass that it's very difficult. Well, it's not difficult to calculate the density, but the density would be such a small number. So rather than taking a milliliter, we take a liter of gas to talk about its density. Well, we have a couple of tables in the chapter that give us the densities of some common materials. First of all, some of the elements, the density of some of the common elements. And as I say, if we were to take a piece of metal, we didn't know for sure what it was, and we measured its density, then we could use a chart like this to try to determine what element we were talking about. Notice here's aluminum, density of 2.7 grams per cubic centimeter. One of the functional properties of aluminum that makes it so valuable in producing things like step ladders and cans, etc., is its low density. An aluminum ladder is pretty light. An aluminum boat, canoe, is fairly light. The reason that it's fairly light, in contrast to if we were to make it, let's say, from iron, we see that the density of the aluminum is about 3 times less than the density of the iron. So if we use the same amount of metal, by that I mean the same thickness, the same surface area of metal, and we were to build, say, a canoe out of iron, it's going to have then a weight about 3 times as great as the aluminum would. And if you were carrying it, if you were porting it out of an area of woods or into a river or something like that, obviously you like the advantage of the thing that's 3 times lighter to carry. Aluminum ladders are lightweight. Aircraft parts, automobile parts. Wherever we can use aluminum as a good functioning metal is an advantage if we want to cut down on the weight involved. Well, this goes on down. We get down here. Here's silver. Gold. Let's take a look at gold. Gold is 19.3. It's pretty dense. Gold is a very dense element. And platinum is even more dense. And if we look at the periodic chart here, we will find that these two, gold and platinum, fall close to each other, side by side actually, in the periodic table. And so we see that there's probably some general trend to changes in densities that relate to position in a periodic chart. Now, we're not going to try to make any predictions, but we can probably see some general characteristics showing up. All right, Mercury, 13.6. So it's a fairly dense material, and remember the thing that we mentioned in our first lecture was that mercury is the only metal that exists as a liquid at room temperature. So it's a very dense liquid. Now, another table that's in the book gives us some compounds, and we'll take a look at a couple of densities there. We have the water. Water is 1 gram per milliliter. And if we look at the rest of those liquids, all of these liquids are less dense than water. Ethyl alcohol, gasoline. In the first lecture I mentioned, did you ever wonder why gasoline and water do not mix? Well, this doesn't explain why they don't mix, but it does explain why, if I put water and gasoline together, if they don't mix, and water is more dense than gasoline as a liquid, where would it probably go when we put the two together? To the bottom. As a matter of fact, we can use density to predict whether something will float or sink when it is put together with another liquid or a solid or whatever the case might be. So density can be used to predict then whether something will sink or float when we combine them. Dry air, now notice we're going to liters here. Dry air, 1.29 grams per liter. Carbon dioxide as a gas, 1.96 grams per liter. We take advantage of that knowledge of carbon dioxide to use it as a fire extinguisher. If I have a fire burning over here on the floor, or say in the trash can over here, something started on fire in the trash can, in order for that material to burn, one of the required chemicals is oxygen. And oxygen is in the air. 19% of the air, roughly, is oxygen. Now, if I take that fire that's occurring here, and I have a carbon dioxide extinguisher and spray CO2, because CO2, carbon dioxide, is more dense, it will sink to the floor. When it sinks down, it pushes the air out of the way. And if we push the air out of the way, we're removing one of the things that's required for the fire to burn, which is the oxygen. The fuel is there, but the oxygen's no longer there to burn it. So the fact that carbon dioxide is more dense than air allows us to use carbon dioxide fire extinguishers. It makes a blanket across the fire which shoves the air up, moves the air above it because the air is less dense, and thus we've removed the oxygen from the flame. And of course we see the reverse case for helium. Helium is about 5 times less, more than that rather, 6 or 7 times less dense than dry air. Well, if we want something then to float in air, it would be good to use something that's less dense in air. So what do we use in our weather balloons? Helium. Or if you go to the store to buy a Valentine's Day balloon or a birthday balloon or a whatever, over-the-hill balloon, something, any balloon, they inflate it with helium, and because it is less dense than air, the balloon will float, it will rise. Okay? And so that's why we use helium. Also, hydrogen is less dense, and hydrogen can be used for balloons also. All right? But hydrogen has a chemical property that makes it a little dangerous to use. Hydrogen reacts very rapidly with oxygen, so if there's a spark or a flame, hydrogen will immediately react with oxygen and cause a chemical change. Helium has a different chemical property. It does not have any tendency to react with oxygen. And so if I take a helium balloon and put a match to it, all I'll do is I'll make the balloon itself pop because I'm going to soften the rubber and there's pressure inside from the helium, but I get no chemical change. I don't get anything happening between the helium and the air around it. Okay? All right, so we can use density then as a way of identifying. And as I say, we can use density or differences in density to predict if something is going to float or sink. Here are two beakers with water in it. We have two identical cubes. Here's a cube of aluminum metal. Density of aluminum metal was about 2.7 grams. And a block of wood which has a density of about 0.7 grams. Because aluminum has a density greater than water, it sinks to the bottom. Because wood has a density less than water, of course, it floats in that case. Also here is an example of the two liquids, and I've mentioned this previously. Here we have a mixture of water and gasoline. Now, the water in this particular case, I added a little bit of food coloring just so that it's easier to see than just the white water. But that's water in the bottom and gasoline. And they separate. Gasoline, if we recall or look at the table, gasoline has a density of 0.6 approximately. You notice that there's a range. It says 0.56 to 0.66, and that's because, of course, gasoline is a mixture. Gasoline is not a compound, so it doesn't have a fixed density. Gasolines at the pump are quite different. As you know, they're rated differently, and they have different compositions. They're mixtures. And so their density varies. But gasoline is less dense than the water, and so it floats on top. If we were to take a piece of aluminum and put it into a beaker with mercury, hopefully we can see this all right. This is a beaker, and this has about 50 milliliters of liquid mercury in it. Now, if I take that same cube of aluminum that I put in water that went to the bottom and put it in here, the aluminum sets on top of the mercury. Now, the reason is that mercury has a density of 13.6. Aluminum has a density of about 2.7. Because aluminum is less dense than the liquid mercury, of course, it floats. All right? So we can use, again, the property of matter of density then to predict whether something is going to float or sink. We can use it as an identifying material. As I say, I could tell the difference between platinum, which has a silver color, and silver by looking at the density. If we go back to the table, we find that silver is much less dense than is platinum. So if I took a piece of the two metals, I didn't know which it was because they're going to look a lot alike, measured the density, I could then determine which one of the two substances we were talking about. And here's another little practical application of density and the fact that things float or don't float. Near winter time, of course, we become concerned with the ability of our material in our radiator to protect our car from freezing, the antifreeze. And here's a little tester. It doesn't look very complicated. It isn't. It's called an antifreeze tester. And the whole function, the whole method of measuring is based on density. Because as we add antifreeze to water, it becomes more dense. The solution becomes more dense. And as the density increases, it turns out that the freezing point decreases. In other words, we're protecting our car from freezing by lowering the freezing point. And all this thing has here is just a little glass tube, and it has 4 little spheres in there, and each sphere has a slight different density. And we have a tube, and we can pull some of the antifreeze up into the tube, And depending upon how dense it is, will determine how many of those little spheres float. If all 4 of them float, it means that the solution is quite dense and we're protected quite well in the antifreeze. If all 4 stay at the bottom, we're not protected at all. We're talking about basically pure water. Well, I'll show you what happens then. I could do it here, but it would be very difficult to see way back there, so we'll do it this way. This is just the empty tube, the 4 balls at the bottom. And what this says is floating balls. This gives us the temperature range that we're protected to, which is the top number there is a plus 20, and then it goes down to plus 5, minus 10, minus 25, minus 40, and that's unfortunately Fahrenheit degrees, not Celsius degrees. But that's the temperature we're used to using, I guess. This is with water. Water has been pulled up in here. Notice that the spheres are still all down at the bottom. None of the spheres are floating, indicating that we're protected less than plus 20 Fahrenheit degrees. Actually, of course, for pure water, we're protected at only plus 32 degrees. And then if I pull some antifreeze up into the tube now, notice that my 4 spheres are now floating. Right there's the liquid level. All 4 of them are floating. And with all 4 of those floating, it means that my antifreeze would protect my automobile to minus 40 degrees. Okay? So again, here's the use of a physical property and understanding of density to make something that we can use commercially. Later in a chapter on oxidation reduction, we're going to talk about electrochemical cells, and when we talk about that, we'll also talk about another measuring device that's based on density, which is called a hydrometer. And we use it to measure the charge on our car battery, for instance, a little battery tester. Same type of principle. So we'll stop here today. Be sure to get the correct text, and we'll see you tomorrow.